So today we're going to move into sections 22-6 and 22-7, which is about switch mode power supplies. Now, what exactly is a switch mode power supply? Let's look at what we've done so far. What we've done so far is shunt regulators and series regulators, and these are known as linear regulators. And the reason for that is that they act like a variable resistor. So in a series regulator, what we're doing with the transistor is we're basically using it like a variable resistor, and we adjust the resistance to get more or less current going into the load, and this is how we control the voltage. So what we are doing is we're operating the transistor in the middle of the load line. And if you recall from your semiconductor devices courses, the area in the middle, this was often called the operating region or the gain region, and it's often called the linear region. So shunt regulators and series regulators are called linear power supplies. So in a linear regulator, we use the transistor like an adjustable resistor, and we operate it someplace in the middle of the load line. However, in a switch mode power supply, what we want to do is we want to operate the transistor like a switch, and then we want to have it flip back and forth between saturation and cutoff. So we always operate either completely shorted or completely open. And in this mode, the transistor will dissipate very low power. So we have a more efficient voltage regulator. One of the problems I have with this circuit is that if I close this switch, then the output voltage across the load will immediately jump up to 12 volts, and we won't be able to regulate it. So in a switch mode power supply, what we do is we operate the transistor like a switch, but we filter the output using an LC network. So we would put an inductor in here and maybe a capacitor, and although at this point here we would see the output going up and down between 12 volts and 0, after the filter network we would get some regulated output voltage which is lower than 12 volts. So the output voltage is smoothed out using LC filters. Now the final point about switch mode power supplies is that the output voltage can then be controlled by pulse width modulation. So if I turn this transistor on and off at about a 50% duty cycle, if I got 12 volts at this end, well then the LC filter will give you something like about 6 volts out. Now that depends on how much current goes to the load, but if it's a light load, then it would be proportional to the pulse width modulation. If I turn the transistor on and off with a 50% duty cycle, you'd get about 6 volts, 25% would get you about 3 volts, and 75% would get you about 9 volts. So by adjusting how often you turn the transistor on and off and what percentage the on time is, you can regulate the output voltage. So figure 22-25 from the textbook shows a DC to DC converter, and this one, it's important to note that this is an unregulated DC to DC converter. The output voltage is not controlled. So down here we've basically got a relaxation oscillator, and it's generating a square wave which then turns these transistors on and off. So basically on the input to the transformer you will have a square wave. You'll have plus minus phases applied to the input of that transformer, and then on the output you will see kind of a square wave sine wave mix on it. It won't be a great square wave because transformers do not pass the DC well, and the flat portion of a square wave is the DC. So what you get out of here is kind of a messy looking sine wave. That gets full wave rectified by the bridge rectifier and then filtered out onto the capacitor. So at this point here you have a relatively flat DC voltage. This one is unregulated. So the voltage that comes out, if I apply more load to it, another load resistor, well, the output voltage will drop, and if I remove the load, it will rise up to some maximum value. Unregulated DC to DC converters have limited applications. Most voltage sources need to be controlled at a certain voltage to be useful. So I've pulled a schematic off the internet to look at how a regulated DC to DC converter works. So first of all, this one is going to convert some AC voltage which it's saying is 220 volts AC into a DC voltage at this end, and the value isn't given. It doesn't really matter what it is. So on the input here, 220 volts AC, that's an RMS voltage, which is down here. So the peak voltage is √2 times that. So this is about 310 volts peak voltage on the input. Now this part right here, this is all an AC line filter. And you can buy this in one package, and it looks something like this. So here, even on the side of this, you can see a little schematic of the inductors and capacitors inside. There's a couple of capacitors on the input, and those are for ESD protection, and then there's an output one for filtering. And then there's what looks like a transformer in the middle, but it's not actually a transformer. It's an inductor that has two coils wound on the same core. So this thing is what's called a common mode choke, and it's essentially two inductors wrapped on the same core. So there's one inductor, and then here's the other inductor here, and they're wrapped on a common toroidal core, and they act as a common mode choke. So if there's noise coming in here on the sine wave, that'll be common mode noise, and that'll get filtered out, but the actual sine wave voltage will get through, and it'll appear at the output of the filter. So the output from the line filter will go into a full wave bridge rectifier. And so at this point here, without a capacitor, we will see the AC line voltage rectified into a 310 volt peak rectified voltage. And that will charge up this capacitor. So across this capacitor, you will have approximately 310 volts all the time. And that'll be a DC voltage. And this is why we call this a DC to DC converter, because the first thing we do is we take the AC and we rectify it. And so now we've got a DC voltage here, 310 volts, and then we put it through a transformer and we step it down to a DC voltage on this side. Hence it's a DC to DC converter. So now we've got about 310 volts on the primary side of this transformer, and then the other side of that transformer is connected to a top 224. Now this looks like a transistor, but if you pull the data sheet up on this, you'll find it's a little bit more complicated. It actually has pulse width modulation circuitry built in, so it will turn that on and off at a certain frequency and adjust the duty cycle. But essentially what we're doing is we're using that part as a switch to create a current through the primary on the transformer. And this creates a current, this induces a current into the output side of that transformer. And if you look at the phase dot, there's one phase dot over here, there's one phase dot over here. So if we create a current in this direction by switching the one side to ground, then we create a current in this direction, which gives us a positive V out at this point. And that V out will be kind of a rough voltage, but then we follow it with an LC network that filters out that rough voltage, and we're left with a nice stable DC voltage. So that generates the output. Regulation of the output voltage is controlled by tapping off some of the output voltage and feeding it back to this diode here. And this diode gets turned on and off by the current through it, which then turns this transistor on and off. That voltage gets fed to the top 224, which then adjusts the amount of pulse width modulation that goes into the transformer, and then that adjusts how much V out is. So it's a control loop that taps off some of the output in order to regulate the input. Another interesting point in this circuit is that there's a second output from the transformer, and this is used to create a voltage that powers the feedback circuit. One of the advantages of a switched mode power supply configured with a transformer is you can see that this ground point here, there is no connection from that ground point to the actual ground on the input side. So there's electrical isolation between the AC 120 volts AC line and the ground of your DC supply. So they're electrically separated, touching this ground, does not put you at risk of shock hazard from the 120 volt line voltage. So here's an example of a switched mode power supply that I pulled off the internet. Let's see how many of these parts or sections we can identify. So first off, this looks like the AC input. That's where we would apply our 120 or 240 volts input. Looks like this section over here is my DC output, and it looks like I've got more than one. There's probably two voltages out, so here's probably plus voltage 1, ground, and here's plus voltage 2 and ground. The AC line filter is over here. This is our toroidal inductor. It looks a little bit different. The shape is different, but basically we have two coils. There's one, there's the second coil, and they're on a common core, which is not a toroidal donut, but it's still a loop. And then we've got a couple of capacitors here. That's part of our input filter. The diode bridge rectifier is this part right here. You can see that there. And that rectifies the voltage and charges up this big capacitor here to about 310 volts peak. Then we've got our transformer and our switching transistor that puts current through that transformer on the primary side, and then it goes out to the output. So this guy and this guy are probably some kind of a diode output that goes into this LC circuit here. This is probably for one supply output, and then that LC circuit is for the second supply output. And then I see a couple of more capacitors here. On the feedback side, I have a 4-pin device here. That's the Opto Coupler. And then what looks like a reference in the other schematic. I think that was a TL431. That's a voltage reference. A couple of resistor dividers. That's your feedback control circuit. In order to pass UL or CSA testing, what you need to do is provide many thousands of volts of electrical isolation between the input and output. And that's achieved basically by putting a big space in the circuit board here. So on this particular one, you can see that the output side, which is this is the DC output side, and this is the AC line input. So that's where your 120 volts goes in, and here's your transformer. So what they do, in order to ensure there's no way you can get a shock by putting your fingers across here, is they put in a big gap in the circuit board, and neither side is connected to the other side. All of the power is delivered by the transformer, and it provides electrical isolation between input and output.